sort of an understanding of what we're about to get into, I made a little list of the strength of either intermolecular forces or chemical bonds in increasing order. So your weakest is your London dispersion forces, then your dipole-dipole, hydrogen bonding, ionic bonding, and metallic bonding end up being tied. And then your strongest is something called a covalent network. Now, it's a little tricky because 1, 2, and 3, you'll see in my note, are talking about covalent bonds. And then we have this new thing called a covalent network. And we're going to talk more about each of these in turn as we go through the slides. We have ionic solids, covalent network solids, molecular solids, and metallic solids. And all of these contain something called lattice points that create crystalline structures. So, for example, salt is always going to make a cubic shape because of the way it has lattice points. Quartz always has a hexagonal shape. If you've ever seen true quartz that has been like at a gift shop or a gem store, it is going to have a specific structure, and it's because of these lattice points. So the first type of solid I want to talk about is ionic solids. These are going to be made up of ions. And so the positive and negatives are going to create a regular crystalline structure. They have high melting point and boiling point. If you want to think about salt, just normal table salt, sodium chloride, if I put it in a pan and try to heat it and melt it, it's not going to. It's just going to sit there. And it has a low vapor pressure. So vapor pressure is just the ability to evaporate. So low vapor pressure means it doesn't evaporate easily. High vapor pressure means it does. And so it has a low vapor pressure because there's strong attraction between the ions. The attraction between the ions, that positive and negative ion, is called an electrostatic attraction. Going back to Coulomb's law, because it never goes away, the smaller the ions, or if they have a larger charge, they'll have greater attractions, resulting in the higher lattice energy. If we remember that equation for Coulomb's law, we have the Q1, Q2 on top over the radius squared, and that's equivalent to our force. So if we get a smaller radius or more charges, then that increases our attractive force between the ions. These are typically brittle due to the repulsion of ions. If I have a salt and I put any sort of stress on it, like I hit it or try to crush it or anything, what happens is if the negative ions all come into contact with each other because we're shifting the structure around, they just break, and that's what it means to be brittle. They conduct electricity only when the ions are mobile, so we have to either melt it or dissolve it. And these are typically going to be a metal bonded to a nonmetal. We've talked about ionic solids in your high school level chemistry class. We're just throwing in a little bit more with the concept of Coulomb's law. This is a picture of an example of sodium chloride. So sodium atom becomes the sodium ion and has a charge of +1. It transfers its electron to chlorine. Chlorine atom becomes chlorine ion, and it has a charge of -1. Size of the atoms, your sodium atom, the ion becomes smaller and the chlorine becomes larger. And then you can see that they're alternating. So you have positive, negative, so that the overall net charge is 0. Covalent network is unique because it is going to have to do with either nonmetals in their elemental form or a binary compound that contains a metalloid. The most common examples that you are going to see AP give you for this is going to be carbon, just pure carbon in any form. So carbon as graphite, carbon as a diamond, just carbon. So that's what it means by elemental nonmetal. So it's just that element by itself. The other option you're going to see a lot is SiO2, which is Sand's formula, or glass. Those are the two most common you're going to see. So these have, they form into what we consider a giant molecule. You'll see a picture here in a minute, a few pictures of what it's going to look like. They have covalent bonding if they are bonded. That has to be broken in order for them to melt. And those bonds are going to be pretty strong in the covalent network. And so they have very high melting points. They're very hard and very strong. You can think about diamonds. They are rigid, so they have very fixed positions, but they're also brittle because the covalent bond angles are fixed. So like when we're writing with a pencil, that is carbon, it is graphite. They also mix in a little bit of clay. But when you're writing with it, you're rubbing off part of that elemental nonmetal. That's what allows us to write on paper, is because it is brittle. So these are some structures. So this first one over here is carbon as a diamond. This over here is graphite. You can see that the structure is very different. So these sheets come off when we write with graphite. Whenever we write, those little sheets come off with each of them. And like I said, it's not pure graphite. Most of the time they add in a little bit of stuff into your pencil lead. And then you see here is silicon dioxide, which like I told you is sand and glass are both of those. Here's silicon carbide. Both of these structures, actually all three of these structures, you'll notice are more of that tetrahedral shape. And then this one is going to be rings for your graphite. Molecular is going to be covalent. So molecular solids are composed of distinct individual units, and they're pretty weak. These things you're actually, so in the thing with these, with your covalent network, the bonds have to be broken. So that's why everything is so high. But over here with your molecular solids, what you're breaking is actually the intermolecular forces. And so you're breaking the intermolecular forces, so either an LDF, dipole, and or hydrogen bonding. Those forces, if we go back to the very beginning, are the weakest. And so covalent solids are not, those molecular solids are not as strong as your covalent network. These have low melting and boiling points. You can think about sugar. Sugar is a molecular solid. It melts almost immediately once it touches heat. They do not conduct electricity because the electrons are held tightly within those covalent bonds. And they can be very large molecules and polymers. So this is an example of ice. So we talked about how these intermolecular forces exist. Ice is water. Water is bent. Bent is an asymmetrical shape. So it is a polar molecule. So you're seeing these attractive forces from your partially positive hydrogen to your partially negative oxygen. And it just, that attractive force happens over and over. And with ice, you end up with them having these empty spaces, which is what allows ice to float in water, liquid water, because it is less dense. Down here is carbon dioxide, would be an example, iodine, and sulfur. Sulfur does something weird where sometimes it can bond to itself 8 times. Phosphorus can sometimes bond to itself 4 times. Some stuff is weird with the different shapes. But these are all considered molecular solids. Last one is metallic solids. These consist of metallic crystals, and these are going to have that sea of electrons. Because of it, they're good conductors of heat and electricity because of the movement of the sea of electrons. They're close packed together, and they're able to be malleable and ductile because they have non-directional bonding. We talked about that before for metallic bonds. And hardness, melting point, depends on the strength of the metallic bonding. Here's an example of those sea of electrons. The first picture is group 1 metals. The second picture are your group 2 metals. So when you're looking at to decide what type of solid it is, you really want to look at the chemical formula. If it is just a metal by itself or an alloy, that would be considered a metallic solid. If it is covalent, then it is going to most likely be a molecular solid. But if it's covalent, it's SiO2 or just pure carbon, then that is a covalent network. And ionic is going to have a metal bonded with a nonmetal. So to decide what properties they have, first you need to be able to recognize from the chemical formula which formula matches which solid, and then go from there with determining the properties.